Good afternoon and welcome to a whirlwind tour of the Niagara Peninsula Borehole Data Release, otherwise known as MRD 383. The Niagara Peninsula 3D Sediment Mapping Project covers 5,000 square kilometers extending from the Niagara River westward to the previously released Brantford Woodstock project. 99 continuously cored boreholes were drilled for the project, 29 of which were converted to monitoring wells. Many factors come into selecting optimal drill sites: geophysical targets, knowledge of superficial geology and quaternary history, as well as the practical problems of modern infrastructure. The boreholes in this release cover a wide range of both sediments and landforms. Before we go any further, I'd like to thank my amazing crew of drillers, students, and everyone at the conservation authorities and municipalities who helped with site selection and the permitting process. So let's get down to business. The data in this release are organized into 6 folders, and we're going to take a peek to see what's inside each one. I'm the first to admit that I got a bit carried away with this release. The explanatory notes ended up more of a report describing the geological setting, quaternary history, and hydrostratigraphic units of the project area. Loads of example photos of the sediments encountered and describing the information found in each folder and file. I would like to draw your attention to the table of contents at the bottom left. Throughout this presentation, I've used green triangles to help us stay organized. High-resolution versions of the maps based on fully attributed seamless thematic map layers can be found in their own folder. All of these GIS products are available for free download from Geology Ontario or OGS Earth. A graphic log summarizing the information found within the analytical data and subsurface database folders was produced for each borehole. The individual logs and source data will be the focus of this talk. Key location and watershed information are shown in the header portion of each graphic log. The complete data set can be found in the borehole location sheet of the subsurface database, as shown by the green triangle at the bottom of the slide. The middle image shows the common legend used on all log sheets. And finally, I would like to draw your attention to the fact that the scale varies with borehole depth. There's a shapefile of borehole locations along with layer files for coloring the holes by presence of a monitoring well, as shown here, or by conservation authority, as shown at the beginning of the presentation. Returning to our graphic log sheet, the first log illustrates where oxidized sediments were observed based on a quick visual assessment of the sediment colors. The symbols indicate where coarse layers or fracture planes were more strongly oxidized. In general, oxidized sediments are yellow, orange, or brownish compared to pinkish brown or gray. Examples taken from the explanatory notes are shown on the right. Of particular interest are the reduced and strongly oxidized halo around a root, oxidized coarser lamination, and oxidization around a fracture. Sediment and rock units where macroscopic evaporite crystals were observed are displayed next. Reprecipitated crystals are observed in overburden cracks and typically have the appearance of granulated coarse sugar, as shown in the upper photos, although larger crystals were occasionally observed, like the one shown at the bottom left. The remaining photos are from bedrock. Intervals with fractures or desiccation cracks that extend from the surface to depths of nearly 10 meters in some instances are displayed next. These intervals, along with those for evaporite crystals, are recorded in the detailed Lathology sheet of the subsurface database. The upper image highlights breakage during drilling, which can be distinguished by sharper edges. Oxidation or mineral precipitation was often observed. Monitoring wells were installed in select boreholes by some conservation authority and municipal partners, and some were later upgraded to nested wells. The remaining holes were plugged. Construction details are shown on the graphic logs as well as listed in the monitoring well sheet of the subsurface database. Hydrostratic units for OGS 3D sediment mapping projects are defined based on age, depositional environment, and lithology. The units are regional in scale and so are time transgressive and typically group multiple facies. The units used for the Niagara Peninsula project dovetail into the broader framework used above the Niagara Escarpment. These units are described in the explanatory notes, and the unit contacts are in the subsurface database. The unit class simply refers to whether the hydrostratigraphic unit is dominantly aquifer or aquitard sediments. Next, we have columns describing the lithology of the borehole. The detailed lithology, supplemented with a column of symbols, is shown on the far right. Since I'm a splitter, I've included a summary version on the left, which reduces over 3,400 detailed descriptions down to less than 1,000 short ones. In between, there's a text log with general descriptions and interpretations. As ever, all of the information is in the subsurface database, and there are examples photos of each facies within the explanatory notes. Photos were taken of the completed borehole of each core, as well as in 25 centimeter increments. Jose carefully cropped and renumbered over 18,000 photos according to the borehole and depth to make things a lot easier for us to find. Look for these photos in the photographs folder. Wood fragments suitable for radiocarbon dating were obtained from 2 boreholes. Dates from the Burlington Bar record increasing water levels in Lake Ontario, while the St. David's Buried Valley dates are from before the last glacial maximum. Information on samples and results are in the analytical data folder, while photos of the fragments are in the photographs folder. The next log records a quick visual assessment of whether the core was disturbed during drilling, like the example shown on the left. Core stretched and twisted by hollow stem augers are shown at the top. The results of a cobble being pushed through soft clay, fluidized silt, and finally the cottage cheese texture caused by gas bubbles are also shown. Naturally deformed sediments are shown on the right. The next group of logs display analytical results from samples taken in the field. All of the results are found within the analytical data folder. Note that the grain size and carbonate bars are shown with standard thicknesses of 30 centimeters, so they're visible on the log, while the pebble lithology bars reflect the sampled interval. A pocket penetrometer was used to measure the unconfined compressive strength, otherwise known as stiffness or hardness, at 5 centimeter increments. Disturbed, fluidized, sand and gravel and rock intervals were omitted. It wasn't long before we noticed that, all else being equal, oxidized and silty sediments were stiffer than reduced or clay intervals. I was a bit of a late believer in this instrument, so the first few holes drilled were not logged, but we still managed to rack up nearly 30,000 readings and often had to rope the drilling crew in to give us a hand. A huge number of grain size analyses were done on diamicton, sand, silt, and clayey sediments. The main spreadsheet is enormous, and there's been a bit of confusion in the past. The first few columns show the borehole, sample number, and sample depth. This is followed by percentage of coarse sand, fine sand, silt, and clay. Next are percentile data that can be used to calculate mean, standard deviation, and skewness. And finally, detailed outputs from the grain size analysis are presented as a percent in channel, which is like the old school percent on a sieve, as well as percent passing. These data can be used to draw grain size envelopes and estimate K values. Carbonate analysis was done on diamicton and fine-grained glacial-lacustrine sediments as part of our fingerprinting efforts. The key data fields are percent and ratio of calcite and dolomite. There is a caveat with this data. The results are influenced by grain size. Pebbles were collected from gravel and diamicton units, a real labor of love given the generally stone-poor diamictons we had to work with. Picture all of us carefully squeezing what felt like miles of core. Once cleaned, the pebbles were separated by lithology and color. This information helps to build up a picture of source area and in turn ice and water flow directions. Many people worked on this over the years, and everyone sees color a bit differently, so looking at general trends is recommended. Photos were taken of each sample, forming a useful way to have a quick check on class size and roundness. Looking at the images on the far right, you'll notice our attempts to overcome problems with mushy shale and weathered crystalline rocks. Simply chuck a bead into the wash bottle. Finally, a group of logs references the drilling method and recovery. Each borehole was started with hollow stem augers and then switched to PQ coring. Split spoons, a tricone, and hydrovac daylighting were also used throughout the course of the drilling programs. The photos on the right show what you might expect to see with each method. At the top we have auger, then a PQ, spoons, and finally a tricone. Putting the data sets together, a number of trends begin to emerge. First, coarser sediments like sand and silt tend to be oxidized more deeply than clay. We also found that oxidized sediments were stiffer. Clayey deposits tended to be softer, and the calcite to dolomite ratios were higher. Silty intervals caused a noticeable increase in stiffness, and there was also a marked increase with older deposits. Other 3D sediment map areas have data releases that include hyperlinks between a base map, logs, and descriptions. Extended explanatory notes, oxidation, evaporates, fractures, deformation, and drilling method logs are new for this project, but the lithological descriptions and analytical results remain fairly consistent. Sometimes additional data sets are included. For example, downhole geophysical logs were included for the Waterloo and Barry projects. The results of heavy mineral analyses was included on logs from South Simcoe and Brantford Woodstock. Hydrostratigraphic units were recorded for the South Simcoe and Orangeville areas, but not for earlier projects. Orangeville has both a borehole data release as well as a magical map, while in Niagara, section and auger sites were released as their own MRD. Basically, we are trying to make these releases as useful as possible and are always willing to try new ideas. To get your hands on all of these great releases, launch Geology Ontario and search the publications database, or launch OGS Earth and download the geological maps and digital data index. Another way is simply to subscribe to the OGS data release notices. And with that, are there any questions?